Okay, so we were at this 1D super resolution example, right, where we had said that we have a signal x of t, right, that is given as sine 2 pi f naught t plus sine 2 pi f1 t. Okay, and suppose let's just assume that f naught is, okay, I'm just taking some values, okay, arbitrarily 4 hertz, and let me say f1 is equal to 4.3 hertz. Okay, that means a difference between the two is delta f, which is equal to 0.3 hertz. Okay, and the whole idea is, right, we want to be able to draw samples from x of t and then use those samples in order to be able to super resolve these two, in the sense that we should be able to resolve both frequencies, right, when you get your xn. Now, first of all, we have to make sure that xn has both the frequencies, and then we have to look at downsample versions of xn, which will run into trouble because they won't be able to reveal these two frequencies. And then we have to use the super resolution idea by taking multiple observations and combining them within a super resolution framework. Okay, right. That is the idea of this example. Now, okay, our sampling rate, in order to avoid aliasing in xn, right, let fs be equal to 10 hertz. Now, in this case, the maximum, so which is of course, which is clearly greater than twice the maximum of the frequency, which is 4.3. So 2 times 4.3 is 8.6. Therefore, we have safely taken fs to be 10 hertz. Therefore, our sampling interval is 1 by 10, right, which is equal to 0.1 second. This is our sampling interval. Now, we have to get your xn. Therefore, xn will be simply x of n times ts, right, where your n should go from whatever, right, and n going from 0, 1 all the way up to n minus 1. Now we have to see what should be n, right? What should be the capital N. That means how long should I really watch this signal x of t in order to be able to say resolve, in order to be able to not lose this resolution ability. Now we know that, right, when you compute a 2D, when you compute a DFT, when you compute the DFT of x of n, the bin resolution, right, in the DFT is going to be fs by n. Okay, it's fs by n, which is nothing but 1 by n times ts. Okay, which is why we say that n times ts is the amount of time for which you are watching x of t. Therefore, the more you watch the signal, then your ability to produce ability to be able to resolve frequencies, right, will be higher. Now, in our case, right, we want this 1 by n delta t such that right, this fs by n should be less than delta f, because that's when we can see these two frequencies falling into say different bins, right? So delta f is of course 0.3 hertz, and our ts of course is actually 0.1. So you got something like, say, 10 by n here, and therefore in order to just play it safe, let n be equal to 64. Okay, because that will ensure that 10 by 64 is definitely less than 0.3. So suppose you take n equal to 64, and now you sample x of t as x of n times ts, okay, and then you got like n equal to 0, 1 all the way up to 63, right, because you got 64 samples. So now this is your x of n, okay, this is the sequence x of n. Okay, now in this, right, you will be able to see those two bins occurring at whatever, right, at inappropriate places, right, because you have to see as to some n times fs by n, right, will give you fs by n is where n is 64, will give you your first frequency f naught, and some other n times fs by n, right, will give you your second frequency, which is f1. Okay, so you will be able to, if you compute DFT of xn, you will see two peaks, right, at those two frequencies. Now the problem is you are going to not get from x of n. Now we will assume that all that we see is y1 of n, right, which will be downsampled and averaged, version of x, averaged version of xn, right? If we do this similarly, right, just as we showed the 1D example, use simply dx, but now d will be 1 1 0 0 0 and so on, 0 0 1 1 0 0 and so on. Okay, and then y2 of n, okay, so for this let's assume some warp of x of n, and again, right, create of warped xn. Okay, now we have to assume some value for, say, delta x for this, so that you can apply the warp matrix and get y2 of n. Now if you interpolate y1 or y2 to the size of xn and try to compute the DFT of y1 and y2, you will not be able to see those two peaks. Okay, because you lost them because of downsampling and averaging, right? Now instead, what you could do is, in order to retrieve x, you could take y1, y2, right, stack them up together, and then, right, you know the matrices. So in one case you have like di, the other case it's like dw1, Now, assuming that, right, you know the exact warp, now what you can do is you can compute x as inverse of this matrix times y1 and y2. Okay, and that will give you back your x. Okay, so in a sense, whatever you lost because of downsampling and averaging, right, you'll be able to say, retrieve the x. Now, one of the things, right, that you will wonder is, what about the warping matrix, right? Who will give me? So in a real image super resolution problem, right, you will ask them, and who will give me the motion? Well, the motion will have to be determined. In the earlier days, how it was done was, you had your LR1, which is one low resolution image, another low resolution image, LR2, all the way up to maybe LRM, right? And what you would typically do is, you would actually use SIFT or any such algorithm, right, that you have in order to be able to estimate the motion. Now, the motion itself was normally assumed to be in plane translation of the camera, right? The camera is just assumed to move on, assumed to follow an in plane translation. Now, why is this so? Because if you have an in plane translation and there was an assumption on the scene, okay, now what were all the assumptions? Okay, when you're doing this, we are making some assumptions. Okay, let's kind of look at what assumptions we have implicitly made. We have made an assumption that it is in plane translation, okay, and the scene to be fronto-parallel. Okay, that means the camera and the camera sensor plane and the scene are exactly parallel to each other, and the scene is flat. Okay, fronto-parallel scene. Okay, so flat scene which is actually fronto-parallel. That means there is no kind of 3D in the scene to introduce the parallax. We have seen, right, what is the advantage of having a fronto-parallel scene? It means that when the camera moves, all the pixels move by the same amount. Okay, because every pixel will encounter the same motion, and therefore you have only tx, ty to calculate. You have a global tx, ty to calculate. Okay, so basically that is the only motion. Otherwise, if you had used rotation or something else, right, then okay, rotation is still okay, but then if you had assumed a 3D scene, then each point will move independently, right, depending upon at what depth it is from the camera, and therefore, right, that will lead to a more complicated situation. These days, people are kind of working on the super resolution for 3D scenes, but that is all very complicated. Okay, let's look at the simplest of cases where you assume a global motion and tx and ty is applicable for, let's say, for the entire image, right? And therefore, this leaves you with two parameters. Or you can even afford a more general motion, so you can go ahead and use SIFT. So typically, right, it's okay to assume tx, ty, and some angle theta, which is again in plane rotation, because right, if you're not able to do a perfect in plane translation, there could be some rotations. But then your warping matrix will then have to be changed here. Then this W should then account for, right, just as you know how to account for any kind of homography. Okay, this will be a simpler case of that, right? You will have to account for in plane translation and rotation and warp x. Okay. Now these have to be found from LR. Now what happens is, but then if you notice, the high resolution, the motion is on the high resolution grid, right? It's not on the low resolution grid, right? You are applying it on X and not on, right? So this is a high resolution grid. Therefore, how do you go from low resolution to high resolution? Theta, for example, right, for the time being, let us assume that we are doing in plane translation. Then, in the earlier days, what they used to do was, if your superposition factor is q, then they'll take the high resolution grid motion to be q times tx and q times ty. It's like saying that a 1 pixel motion in LR is equivalent to a 2 pixel motion in the high resolution grid if the factor of super resolution is 2. Okay, which seems reasonable, and that is the way people used to compute motion from low resolution observations. First, sample them up by a factor of q, and then use that for the high resolution warping. Now, this is the way it was done in the olden days. Okay, but then in the last 10 years, I mean, things have changed. Now people now, right now, they see generalization of the problem. Right now, what are the recent trends? Okay, the recent trend is to sort of allow for general camera motion. Okay, allow for general camera motion. So general camera motion. So really don't really say restrict yourself to simply an in-plane translation or something. And the scene is still pretty much flat. Okay, and fronto-parallel. Now this hasn't gone. Okay, the maximum that has been done is 3D. Okay, now well, some works okay assume layered 3D. Okay, what that means is layered 3D. That means, okay, you have a 3D scene, but then, right, they're all like, various fronto-parallel layers, and something is in the front, something is in the back, something is even further back, and so on. So the advantage is that, if you have a situation like that, then the translation factor simply scales. So if you find for one layer, then you can basically find for other layers, by simply translating, by simply kind of taking the depth to simply translate to a scale factor. Okay. And the other thing, right? So all these are complicated ones, right? We are not going to kind of go to the details of this, but I'm just trying to throw some hint upon what is going on. Other thing is joint motion and image estimation. Now, right, this is important because if you really look at it, right? If you really look at it, people, right, don't want to do motion first and then whatever, scale it by a factor of q and then use that on the image, because if something went wrong during a shift or whatever that you're using to compute motion, then that will remain fixed. There's no way to change it. You just blindly believe that the motion estimation is correct, and therefore when you try to invert whatever, right, when you solve for x, your x will kind of, all the errors that you made in the motion estimate will kind of creep into x, and therefore x right will no longer look as nice as you might want it to look like. Now, that is why people do a joint motion estimation, motion image. That means in one iteration you solve for motion, in the other iteration you solve for the image, and then you keep on updating both. Okay. Now, which is like an alternating framework. As far as the image is concerned, people are using priors like the L1 prior and so on that I already mentioned. The observation model, right, will still be norm of y minus. The observation model will become y minus dwix norm square and summed over all I. Okay. Now minimize over x and the camera pose. Okay, so what you have is plus some gamma times, then you'll have a prior for the image, prior for f, and then you have plus a prior, let's say beta, a prior for well, I mean, what you typically do is, of course, you alternate, and in the sense that you don't have a prior here. Now instead what you have is, okay, this is when you solve for x. Okay, and then you alternate, right? Next time you solve for the camera motion p, okay, because right I and then norm of y minus dwix square plus, let's say, beta times a prior on camera motion, right? This will be typically sparsity and so on. Okay, so a sparsity prior, and this p is the one, right, that will sit in this warping matrix. Okay, so what are those sparse camera poses that you have in order to be able to get these warping matrices for each of these x's. The other reason why this is done is because if you simply upsample by q, right, this tx and ty taking the q, it's actually incorrect. It's not correct, because then this assumes that LR2 can be exactly identified from LR1. But then the whole point is, if that is the case, then you actually cannot do super resolution, because LR2 does not carry anything new. Right? No, between LR1 and LR2, there is nothing new. That was a pathological case that I mentioned. For super resolution to happen, LR2 cannot be identical to LR1. Therefore, the TX and TY that you actually calculate may not be correct, because these two images are not identical. They are not just shifted versions of each other. And therefore, multiplying by QTX and QTY, you're already making an error, right, in terms of what estimates for the motion you are taking. And therefore, the recent trend is to actually do what's called joint, right, motion and motion and image estimation, and this is the way it is all done. And so it's a very nice problem, very elegant, and as you can see, right, brings in all the prior, brings in all the observation model that you have, and tries to undo these effects. Okay, here is an example, right, that I'm going to show you. Okay, here is a super resolution example that we have done, okay, in our lab. And right, as you can see, okay, these are your low resolution observations, okay, and as you can see, right, you're not able to read them that very well. And if you take these, typically what can also happen is, one more thing that I should add is, when you move, right, you could also incur some kind of a motion blur. And therefore, the recent trend is to not only solve for LR images, the HR image, but also assume that the low resolution observations are also blurred, motion blurred. And therefore, if you see that these images are slightly motion blurred, and you're not able to read them very well, read the text very well. There are multiple observations, all of them low resolution. Then the high resolution image, right, looks like this. And here, of course, you're able to start reading 3D geometry in painting, and then kind of you're able to read whatever else is there in that text, right, filling up off, you see, right. There is a missing, right, information and so on. Those things are very difficult to read here. Now, if you go further, right, in the next example, right here, this is one of the malls where my student went and kind of captured some pictures. So see, these are 4 low resolution images, and here is a high resolution image constructed over them. And clearly, right, you can see a lot more details here as compared to this. And here we have shown the low resolution patches zoomed up, and here is the high resolution patch for each of those low resolution patches. and we have also compared with some other methods. Ours is sitting here, and you can see that, right, the Steve Mad and then Truly Tech and so on, which is very difficult to read in the LR, right? You're able to see. So here it's hardly, one is hardly able to see Truly Tech, whereas here you're able to see that. And then here, right, it's with some difficulty you can see Steve Mad, whereas here it's much more clear, right? So basically, such is the ability of this super resolution algorithm. Now here is one more. Here is a video that I'm going to play. Right, let me just play this video for you. And here, right, what you see is really a video where you see this white Ambassador car. You want to be able to pick up the number plate of this car, and if you try to use low resolution observations, you're not able to make much out of them. Therefore, we try to apply the super resolution idea on this video. Similarly, the other one, here is this Maruti car. That's that is the blue colored car or whatever, right? We wanted to get its number plate. Now, if you see, if we directly use the low resolution frames and then crop the number plate, this is what you see. It's very difficult to make out what it is. And even here, the last digit, even though it looks like A835, but the last one could be 2 or 4. It's not very clear. Whereas if you do super resolution, then the first one becomes TN72, some F5757. Now we do not know whether that really is a number, but then it's much more clear than this. And TN makes sense because right, it was actually a Tamil Nadu vehicle. So therefore, to carry TN, right, it makes a lot more sense. Therefore, it has done something good. The other one, right, once you super resolve, there's no doubt now. This is no longer 2. This is clearly 4. Okay. So you can see the ability of the super resolution algorithm, and now, okay, it's also very important in several areas, especially if you're doing some kind of medical imaging, right, where you want to see finer details. Even if you have a high resolution picture, you may want to blow it up further super resolve in order to be able to see finer details and so on. Okay, therefore, okay, this is an exciting area. A lot of research going on, right, even in this, and of course, right, it is impossible to cover all of that, in a course like this. But I hope, right, you have an idea, right, you have really a good idea about how the super resolution idea works.